Welcome to Algorithms with Professor Caleb. Today I'd like to talk to you about data compression using Huffman code. So data compression is an important concept because disk storage is limited, and even more importantly, network bandwidth is limited. So we use data compression to make our files smaller, either because we're storing them long-term perhaps, or even more frequently, we're wanting to make them smaller so that we can transmit them more efficiently. There are many approaches to compressing data. What I want to talk about today is exploiting frequency, specifically frequency differences. So when we think about how we usually represent characters, we typically are using a standard amount of data, 1 byte, 2 bytes, depending on our specific encoding, and maybe up to 4 bytes. But we're pretty consistent across specific character values within a given encoding or set of characters. In most text, however, character frequencies vary widely. For example, in English, if we have much text, the letter E is probably very frequent. The letters Q and Z are likely to appear very little, if at all. The idea then is that we're going to save space by using shorter representations for very frequent characters, so example E in English, and longer representations for very infrequent characters. This is going to allow us to represent all of our different data, but use less space total. We're also going to get some savings from the fact that many of our documents aren't going to use all of the possible characters. So we're going to have fewer characters to represent to start out with. So the kind of code that we're going to use is something called Huffman code. This is a specific approach to exploiting these character frequencies, which is guaranteed to be optimal, given that we're doing character frequency and handling our compression this way. It's not going to be the optimal compression for all data, but it will be the optimal compression for this approach to compressing the data. So the idea here is we're going to first read the file to be compressed and just count character frequencies so that we know here are the characters that show up in our file, and this is how frequently each of them shows up. Once we have that information, we're going to produce the optimal code with variable length encodings based on that frequency. And of course, we'll go into much more detail about how we do that. Once we have that code, then we're going to encode the file, reading the file again, and provide the code itself at the beginning of the output file. Because this code is going to be specific to this particular file. So we do have to also provide the code at the beginning of the file. In general, with a file of some length, we will get enough savings that it's worth it, even though we have to include the tree. Then we're going to recreate the code from the information we provided at the beginning of the file and decode the file when we want to decompress it. Now, the key piece of Huffman code is the code tree. So what we're going to create is actually a binary tree where we have characters at the leaves of the tree. The nice thing about the characters being guaranteed to be leaves is that no code for a given character is a prefix of another code. So we know that if we just go through this code and follow it, we'll eventually get to the right character. The way we produce the code is if we start at the root and go to a leaf, anytime we go left, we consider that a 0. Anytime we go right, we consider that a 1. So in this particular case, the code for E would be 1. The code for M would be 0, 0, 1. And here is the table that corresponds to this code tree. So we can see the set of bits that we would use to represent each of these characters. So D would be a 0, then a 1, and F 3 zeros. So let's see how this works going through an example. So I have here a simple little message, banana hammer. And the first step is going to be to compute the frequencies for all of the characters that appear in our message. So we have 4 A's, 1 B, one E, one H, two M's, two N's, one R. And then I've also added an end of message because we do need some way to recognize that we've hit the end of our file. Once I have the frequency table, then I need to actually build my code tree. So the basic idea here is that I'm going to start by creating a node for each character. So I'm basically going to create a forest of trees, each of which has one character. I'm going to put the nodes, the roots of all those trees, into a priority queue based on the frequency for that node, which in this case is going to be the frequency for the character. Then as long as I have more than one tree, I'm going to take the two lowest frequency nodes, so the lowest frequency trees that I have, and I'm going to give them a parent. Make a new node, adding the two frequencies together for the frequency of this subtree, basically. And then I'm going to put that parent back in my priority queue. So let's see what this looks like with our example. First, let's set up our priority queue. So we have our frequency table. We're going to make a node, basically a tree root, for each of these characters, and we're going to put all these things into our priority queue. Once we do that, then of course we're going to go into our loop. So we pull the B and the E off of our priority queue, and we create a new node to be the root of a new tree that has the B and the E as subtrees. So its frequency is 2. So then we'll add our new node to our priority queue. Then we need to actually take the next pair. So we're going to grab the H and the R, which are the next two items from our priority queue. We're going to make their parent T1, which will be also priority 2. And then we will add that into our priority queue. Then we'll go on. We take the end of message and the M. Our new node will have frequency 3. We then will put that into the priority queue. Then we'll take the next two nodes off, the N for 2 and T0, and we'll build T3 to be the root of that tree. Put that in our priority queue. Then we'll grab the next two nodes, make T4 to be the root with those two subtrees. That has frequency 5, so we'll add that to the priority queue. Then we grab the next two, which will be A and T3. We build that node. Then we add the new node to our priority queue, build the new tree from those two items. Now at this point, we put the node back on the priority queue. It's the only thing left. When we see it's the only one left, then we know we have our final total code tree. So here is the tree we would build from our message banana hammer. The next step will be to actually create a code table from the tree. So we're going to go through each of our characters and basically go through the tree, do a traversal, and find the code and note for each leaf, this was the code to that character. So we'll end up with A being 1, 0, B is 1, 1, 1, 0, E 1, 1, 1, 1, H 0, 0, 0, 0, and so on. So once we have the code table, it's a fairly easy job to actually encode our message using the table. So we're going to go through each character of our message and put in the code from the table for that character. So B will be 1, 1, 1, 0, A will be 1, 0, N 1, 1, 0, A 1, 0 again, and so forth through the whole thing. And of course, when we get to the end of the message, we'll tack on the 0, 1, 0 for our end of message character. Now we do have one other complication here, and that is that we don't write bits to files. We write bytes to files. So we need to deal with these as bytes. we will need to take our sequence of bits and separate it out into bytes to actually write it to the file. Fortunately, in most programming languages, there are certainly libraries available to help you do that, as well as bit operators that will let you operate on the individual bits of a byte. So we can see here that we're going to take our message, break it up into bytes, and write each of those bytes in turn. Now, we do have one other issue, which is that often our messages don't end at an even byte boundary. So what we're going to do is to simply pad that byte on out. Usually with zeros, though it really doesn't matter, because we're never ever going to look at those bits when we're decoding our message. We're going to be able to avoid that because of that end of message character that we included in our code. So at this point, we have our message, we can write it out to a file. We then need to deal with what do we do when we get to the other side. So we are going to need to decompress our Huffman code tree. So we're first going to need to put information about here's the structure of the tree so that we can recreate it on the other end. We always consider that. And when we decide how much we've compressed our message, we always include the amount it took us to express the tree on the other end. Now on this end, we don't bother with the table. We only use the tree that we were using. So what we're going to do is we're going to start at the first bit of the encoded message. And until we have decoded the end of message character, we're going to start at the root of the code tree. And until we're at a leaf, we're going to go left if we've got a 0, right if we've got a 1, and go to the next bit. When we get to the leaf, we're going to record that character. We've gotten to the end of a code that represented a character. So we say, okay, we got that character. Let's go start over at the root for the next character. So let's go through the process of actually decoding, decompressing our message that we created. So here we have our message. We're going to start at the first bit and at the root of our code tree. So then we're going to go right because our first bit is a 1. Then we'll go right again because we have another 1. Then, of course, we have another 1, so we go right again. And then finally, we're going to get to a 0. So we'll head left and we find the B. So we've got our first character. Now we need to start over at our root. We're at a 1 again, so we head right. But this time we have a 0, so we will now head left. And we get our A. That gets us another character, so now we need to go back to our root. We're going to head right. And then we will see that we need to head right again. Then moving on from T3, we have a 0. So we're going to head left now to the N. That gave us a new character, so our next step is to start at the root, where we head right again. And then we're going to head left, and that's going to get us another A. So back to the root again. We're going left, or we're going right again. And we can see that we're going to head right, and then our next character is a 0. So we're going to find ourselves with another N. Then we're headed right. And then we can see that we're going to go left and pick up the next A. Then the next time we're going to go left, left again. and then left again, which will get us our H. Now we need to start back at the root. So we're headed right. And then we're headed left. And we're going to pick up that next A. Then we head left again. So we're at T4. This time we're headed right from T4 to T2, and then right again, where we're going to find an M. And we do actually the exact same thing. We're going to head left. We're going to head right. We're going to head right again and get ourselves another M. In this next case, we've got an E, right. So for the 1, we have another right with another 1. Then we have another right. And yet another right, where we're going to find our E. We're going to head left to T4. We're going to head left again to T1. Then we're going to head right and pick up that R. Then we're back up at the root with the left. So we're back over to T4. Then we're headed right. Giving us T2. And then we're going to head left, where we're going to find our end of message, and our message is complete. Now notice here, we have those 3 extra padding bits that we put in. We haven't used those. We don't even look at them because we have our complete message. So this is why we can easily pad. We use that end of message symbol to tell us we don't have to worry about anything else. Thanks for watching. I hope that helps you get an idea of what Huffman code is all about and how it actually works, the creation of the tree, the encoding, and the decoding piece. Hope to see you next time.